Professor Jinhui Li, who is a professor at School of Environment in Tsinghua University. He is the chief scientist of the Circular Economy and Urban Mineral Innovation team of Tsinghua University, and also serves as the executive director of the Basel Convention and the Stockholm Convention Regional Center for Asia and the Pacific. He is the director of Circular Economy branch of the Chinese Society for Environmental Sciences. And his key research areas include global environmental governance, international convention on chemicals and waste, solid waste management policy and standardization, solid waste recycling, e-waste recycling. He published more than 250 articles in academic journals. And today he will be talking about selective recovery of lithium from a spent lithium-ion battery by mechanochemical induced solid phase oxidation. Professor Li.
Thank you very much, Dr. Amiri. And I would also give thanks to Professor Li Ju for the invitation to this very important conference. So, ladies and gentlemen, good evening. It's my pleasure to participate in the 20 MITAB Applied Energy Symposium. The contents of my report is introduced the situation of global waste lithium-ion batteries, recycling, and some recent work of our team. I'm also introduce mechanical technology that we developed to selectively recover lithium from spent lithium-ion batteries through a case study. So my presentation is a little different from our previous presenter. It's directly related to energy, but my presentation is recycling for the equipment or products used in energy sectors. So as Dr. Amri already introduced my research field, including the waste management and the policy, and also including the recycling and disposal technology of solid waste, and circular economy and urban mining. So my presentation will focus on the 4 parts. One is the global trend in the recycling of spent lithium-ion batteries, introduction of recent work, and the third is the introduction of mechanochemistry, and the last one is about the release of the lithium from spent lithium-ion phosphate battery. Is as a case study. So this is the first part of my report, Global Trade in Recycling and Spent Lithium-ion Batteries. In the reasons why we want to recycle spent lithium batteries. Here you could see that in recent years, driven by development of global new energy vehicles market, the power battery field has become the main factors driving the rapid growth of global lithium-ion battery market in the recent years. Lithium-ion batteries are recognized as the most promising new energy power batteries. The result in this figure shows that the field of new energy-powered vehicles has become the main driving force for the rapid growth of global lithium-ion batteries production in recent years. So in general, the life cycle of lithium-ion batteries are about 4 to 6 years. At the end of this life cycle, the spent lithium-ion battery will enter the recycling chain. This figure shows the global lithium-ion battery recycling market size and future trends. In 2018, the global lithium-ion battery recycling market reached more than 100,000 tons and is expected to reach more than 600,000 tons in 2025. According to the report released by the International Market Research Organization Market and Markets, the market scale of global lithium-ion batteries recycling is about 1.5 billion in 2019, and is expected that this data will increase to 12 billion by 2025. So there are three major motivations for spent lithium-ion battery recycling. One is environmental protection needs. The second one is economy needs. So because we can recover some material from the waste batteries compared with extract them from the original mine is much better from the economy side. And of course, when we have the recycling activities, we need policy support. It cannot automatically to be recycled without the policy support. So this figure is the scheme diagram of the upstream and middle downstream industry chain of lithium-ion batteries. Upstream includes the mining and manufacturing of raw material. The midstream includes the production and the manufacturing of battery compounds, companies, and assembly of lithium-ion batteries. Downstream is the application scenario of lithium-ion batteries. The rules of recycling at the end can be stabilized the industrial supply chain of lithium-ion batteries. The figure in the left in this slide, we can show that the main electrode material type and main application scenarios of lithium-ion batteries. It can be seen that there are four main steps of electrode material for lithium-ion batteries, namely lithium cobalt oxide, lithium magnet, lithium iron phosphate, and nickel belt manganese ternary material. The diagram on the right shows that contents of valuable metal per ton of spent lithium-ion batteries. In recent years, scientific research on the recycling of spent lithium-ion batteries has increased. Most of these studies has focused on how to develop efficient, clean, economical technology to achieve selective extraction and recovery of valuable materials from spent lithium-ion batteries. So in this section, the introduction of recent work, I will introduce some of the projects we are implement and some papers. Our achievements are mainly divided into three parts: pollution control of fluoride in spent lithium-ion batteries, the development of dismantling equipment for spent lithium-ion batteries, and the selective extraction and regeneration of valuable materials in spent lithium-ion batteries. So since 2013, we conduct a series of projects funded by different donors. Some of them is funded by a National Science and Technology Support Program, it's national level. And we're also supported by UNEP for some investigation and assessment of the batteries. And also we are funded by industrial sectors also, such as Toyota, such as the Lithium Group, and Volkswagen. They have China office. And we're also supported by the Beijing city government. Is a major project of Beijing Social Sciences Fund. It's mainly focused on the collection system establishment. And recently we are implementing a project funded by Toyota. The project on research of the whole process management of power battery recycling, with the participation of 6 teams from the Tsinghua University, including School of Environment, Department of Electrical Machinery, School of Material, and Institute of Nuclear and New Energy Technology. So in this project, we are including 4 main research contents. One is the recycling mode and environmental benefit evaluation. The second one is the evaluation system of Electron utilization application. The third one is a green technology system of metal separation and recovery. And the fourth is feasibility of renewable material use in new batteries. So recent years, we also publish papers here. I checked that we have 13 papers directly working on the lithium and batteries recycling, including 1 paper from a Journal of Clean Production, 3 papers from the ACS, Sustainable Chemistry and Engineering, and also 3 papers from the Journal of Hazardous Material, and 2 papers from EST and other journals. For 4 papers is published from our group. So for the 3 papers in ACS, Sustainable Chemical and Engineering, their title is for the from a lead paste to high-value nano-lead sulfate products, a new application of mechanochemistry in the recycling of spent lead-acid batteries. And also we have papers facile, environmental friendly and low temperature approach for decomposition and polyvinyl lattice fluoride from the cathode electrode of spent lithium-ion batteries. And also I have another paper is efficient separation of aluminum foil and cathode material from spent lithium batteries using a low temperature molten salt. So here is a series of papers published by us using mechanical method to recover valuable metals in spent lithium-ion batteries. The title is acid-free and selective extraction of lithium from spent lithium-ion phosphate batteries, where mechanochemistry induced isomorphic substitution. This is published in the EST. And another paper is unveiling the rules and mechanisms of mechanochemistry activation on lithium cobalt oxide powder from spent lithium-ion batteries. It's also published in EST. So we also have some innovation pens related to lithium lithium-ion batteries, such as the recovery of cobalt from spent lithium-ion batteries, method and devices for recovery of metals from spent lithium-ion batteries by water-soluble ionic liquids. And the third one is a method and devices for recovery and treatment of waste lithium-ion batteries with oxalic acid as an extraction solution. And the fourth one is a method for direct regeneration of a high purity lithium carbonate from waste lithium-ion batteries. So in recent years, our main research work can be divided into three parts. The first part is to realize the recovery of fluoride in spent lithium-ion batteries by developing different growing process. In the lithium-ion batteries, the presence of the organic binder polyvalence fluoride, also named PVDF, between the cathode material and the aluminum foil end. The separation of the aluminum foil and the recovery of the cathode material powder. The traditional process of degrading PVDF will lead to the release of fluoride and the environmental risk of dioxin. In order to resolve this problem, we conduct a deep research. So we have developed spent lithium-ion battery dismantling and pre-treatment technology and equipment, and realized the integrated process of spent lithium batteries from pre-discharge dismantle to end valuable material recovery. As can be seen from the figure, cathode material powder, aluminum foil, and copper foil can be obtained by discharging, crushing, and sieving. At present, our research focus has converted from the crushing and separation of spent lithium-ion batteries to the extraction and recovery of valuable metals. Regarding to the recovery of valuable material in spent lithium-ion batteries, in order to solve the technical defects of the traditional recycling process, we have designed a series of environment-friendly recycling process for valuable metal in spent lithium-ion batteries using emerging technologies such as mechanochemistry method. So according to the type of the cathode material, spent lithium-ion batteries can be divided into lithium-ion phosphate, ternary nickel belt manganese, lithium magnet, and lithium cobalt oxide. Our idea is to dismantle the spent lithium-ion battery first, and then obtain the cathode material powder. Subsequently, with the help of mechanochemistry complexation, by adding different ligands and valuable metals in the cathode material are converted into metal products for recovery. Valuable metals in the cathode material powder can be converted to water-soluble metal compounds and the action of mechanical force. Through the regulation and control of the solution, metal products with a high economic value can be directly obtained in the whole process. There's no use of acid and alkali, and no organic waste liquid is produced. And the premise of the guaranteeing profit, high economy profit, can be promoted industrial recycling and resolve the environmental protection and economy cause the problem of the recycling of spent lithium-ion batteries. So this is our route of using mechanochemistry method to recycle spent lithium-ion batteries. The process is mainly divided into above steps, considering the diversified types of cathode material. It is necessary to select appropriate ligands and control process. We have previously divided a series of ligands to assess the conversion of valuable metal in the cathode material of spent lithium batteries into the metal products, such as organic ligands and inorganic ligands. At the same time, during the recycling process, we focus on the following aspects: environmental friendliness, economic benefit, and the migration and the transformation of metal species. So the third part, I will introduce the selective release of lithium from a spent lithium iron phosphate battery. So here is information that for the Mechanochemistry founder information. So I will not introduce much more. This is the history which who proposed this method and what is development of the this technology. Mechanochemistry mainly referred to the application of mechanical energy to condense matter, such as solid and liquid, by means of sharing, friction, impacts, extrusion, etc., to introduce change in its structure and physical chemistry properties and induce chemical reaction. Unlike ordinary thermochemical reaction, the powder of the reaction is mechanical energy rather than thermal energy. So the reaction can be complete without harsh conditions such as high temperature and high pressure. So the above figure shows that the reaction equipment for mechanochemistry reaction. Generally, the mechanochemical reactors play the key roles in the mechanochemistry, and typical. The equipment used for mechanical activation include tumbling mill, stirring ball mill, and vibration mill, rolling mill, and planetary ball mill. So in the past decade, mechanical chemistry technology has developed rapidly in the recovery of valuable metal from electronic waste, such as spent lithium batteries, with PCB, CRT LED glasses, and fluorescent lamps. The first of these technologies is to take spent lithium iron phosphate batteries as a research object. High purity lithium phosphate, iron phosphate, and sodium sulfate products can be obtained by using the mechanical chemistry assisted solid phase oxidation, pure water leaching, and chemical precipitation is happen. The technical characteristic of the process are as followed. The first is short reaction time, the high production. Second one is the high production value. The third one is the high production purity. The fourth one is a shortcut recovery process. And fifth one is no acid and alkali reagent. And the sixth one is achieving zero waste strategy. So this slide, the figure is an experimental flow chart of this study. In the following description, I named the lithium ion phosphate, including this material, the solid phase reagent sodium, and name that PS reagent, so that we can much easily to understand the so complex formula. In the result of the research is show that we first study the solid phase oxidation behavior of lithium in spent lithium battery and the mechanical condition. Figure 1 is a XRD pattern of the beginning new material. As we can see from figure 4.3 as the battery material, the crystal structure of lithium iron phosphate cathode material are not obvious compared to sodium persulfate, and therefore the characteristics, diffraction, and peaks of lithium iron phosphate in the XRD pattern of the mixed samples. Sodium persulfate divided by slash lithium iron phosphate were not significant. This can be attributed to the mixing effect of sodium persulfate. The result of this figure show that XRD characteristics diffraction peak of sodium persulfate slash lithium iron phosphate decrease with the increase of the rotary speed. The peak position of the diffraction peak change significantly. And this indicates that under action of mechanical force, sodium persulfate and lithium iron phosphate underwent mechanochemistry reaction, resulting in a new crystalline phase. Decrease of XRD diffraction peak can be attributed to the mechanical damage to the reaction sample, which led to grain refinement and the latest distortion. So here also show the RDF pattern of the sodium persulfate slash lithium phosphate sample of the mechanical reaction at 600 RPM. So here is the result. And this figure also is show the FTL spectra of different reaction sample. The result in this figure also show that similar to the XRD result, the intercept of the infra characteristic peaks of sodium sulfate are greater than those of lithium iron phosphate. So the result of this figure shows that after the mechanical reaction at different rotary speed, the character peak of sodium persulfate gradually disappear, and the new characteristic peak appear in the infrared spectra. So this figure is the XPS spectra of iron to be before and after mechanical reaction of sodium p-sulfate with lithium iron phosphate. The results show that after the mechanochemical solid phase oxidation, the characteristic bending energy of the iron to be show a significant shift to the right. So this information shows that effect of different sodium persulfate / lithium and phosphate mass ratio on metal recovery. When the mass ratio of this is 2 to 1, the recovery of lithium was able to reach a maximum of more than 99%. At the same time, the recovery percentage of iron is only about 20%. So the result of this figure shows the increasing of rotary speed can simultaneously increase the recovery of lithium and iron, but the effect on N was significantly higher than that one for lithium. So this figure shows the metal recovery efficiency with different ball molding times. The result of the study shows that the for 5 minutes is sufficient. So this is the XRD pattern of water leaching residue. The identification results show that water residue are iron phosphate products. So with sodium phosphate as a precipitant, lithium sodium phosphate in the solution can be recovered by chemical precipitation to finally obtain lithium phosphate and sodium sulfate products. So the economy from the research, very briefly, we can say the economy feasibility is determine the prospect of industrial application of proposed process. Therefore, the economy of the proposed process was also analyzed. So it's comparable, it's a good economy performance. So based on this, we can very briefly conclude that the first is when the solid phase oxidant persulfate was used as a co-grinding agent, 99% above of the lithium in lithium iron phosphate could be selectively released from the olivine framework of iron phosphate and convert to water valuable lithium sulfate, while sodium persulfate was converted to lithium sodium phosphate. The second one is precipitation recovery of lithium phosphate released by chemical assisted solid phase oxidation can be achieved by using water leaching and sodium phosphate as precipitant. The third one is a mechanochemistry assisted solid oxidation system proposed in this study, maybe a new environmental friendly system that could selectively release and recover lithium from spent lithium iron phosphate material. So we can very briefly conclude the presentation. I would like to say lithium battery is a major research of the research team of circular economy urban mining in Tsinghua University. And a broad networking has been established previous year on recycling and collection of lithium batteries. And also we have technology have been close cooperated with the companies of lithium battery recycling for material recovery and dismantling. And also we're looking forward to the cooperation with the famous university and the companies in lithium battery recycling. And also we want to establish a policy and regulation for the collection system. And we also, of course, is a reading fund for capacity building and for developing countries in the future will be high priority to resolve this problem. Thank you very much. Finally, I would like to look forward to cooperation with you and with the other partners. And now I want to conclude my talk and listen your question. Thank you.
Thank you very much, Professor Lee. It's a very interesting talk and very timely. Everybody is talking about how we can recycle batteries, especially lithium. So we have the first question from Julie. He's interested in the fluorine recovery introduced at the beginning. So what's the final waste form and what percentage of fluorine will be captured?
Okay, for the fluoride is currently I have no very detailed date, but I think my postdoctoral researcher maybe here, he can give you through the talk, give you some message if anybody interested. In this stage, we are trying to, for fluoride is not recovery, it's mainly for avoid the environmental pollutants. We much focus on the high valuable materials such as the lithium and the cobalt. And we are more focused on if we could have such as the material could be directly to use for the production of lithium batteries. So maybe it's not recovered to the purified metal and material, but it could be a mixture so that it could be used for the lithium battery material. Thank you very much.
Thank you. So I have a couple of questions. So the first question I have is about the energy consumption. So on your slide 38, you said that you can separate almost 100% of lithium. What is the energy consumption of that? And when you also you said that this is an environmental way of recycling. So did you do any life cycle assessment?
Okay. So for you mentioned a very detailed information from this research. Of course, we can have the calculation of the energy from the laboratory work. So our research currently is more working on the laboratory level. So it's we have some calculation for the energy consumption, but actually it cannot be applied to the industry scale in this stage. So I think at this stage we can provide you some information, but this is a very early stage.
I have one final question. So, as you also mentioned in one of the earlier slides, there are many chemistries for lithium batteries. So, can you apply the same method to different chemistries? And do you think you will get the similar results, or it's very chemistry specific?
Okay, so this is a good question because it's the factories have much type of brand of batteries. That is a challenge. So I think it's currently we are trying to use a different type of lithium battery to have our research. So probably it could be influenced the purity and the efficiency of the material recovery. But from the theoretically, we can see that could be work for different type of batteries. But of course, all the data maybe will be updated if the lithium battery is different. Thank you.
Thank you very much. So we are getting close to our closing time. So it was a very interesting session for me, innovation session. We started from wastewater recycling or recovery of different materials from wastewater. We moved to CSP plants and using CS pond as a cost-effective way of performing producing dispatchable electricity. And finally, we had a very nice talk about the lithium-ion battery recycling and recycling different materials using mechanochemical approaches. I would like to thank all the speakers, Professor Jason Ren, Professor Melanie Tetrofriend, and Professor Jinhui Lee, and as well as all the attendees. Julie, if you have any closing remarks, please go ahead. Otherwise, I think we are done for the day.
Yes, thank you so much, Emery, and thank you for sticking to the end. This is a very interesting innovation keynote session, so I really appreciate it. So anyone has comments or feedbacks, now is a good time to unmute yourself.
Thank you very much, Emery, for organizing this.
Thank you, Melanie, for...
It's a great session.
Thank you very much for the work of organizing.
Yes, so I'll see everyone tomorrow at 8 a.m. Boston time. So have a good evening, have a good day. See you tomorrow. Thank you.
Thank you.
See you. Bye-bye.
Bye-bye.